4.2 Graphs of basic functions. We will learn the basic functions, and we will look at their properties and the graphing piecewise defined functions. Now the first function is the constant function. The constant function's formula is, its expression is given this way: f of x equal to, let's say, 5, for example. It's just an example here. Now, it means for any x value, it's equal to 5. The output is only 5. So whatever you put here, it's just 5. You can't put anything here. So there's only one output, and the x can be anything. So its graph will look like this here, the horizontal line. So you can think of this line here, y equal to c. It's a horizontal line at the level of c. C here is, you can take this as c equal to 5 here in this example. So you see 5. Now, so we will call this one c, okay? Now c is a fixed number, and we will check the domain and the range and the other properties. Okay, the range is clearly there is one output, and this is c. For any x, there will be c as an output. And the domain is all real numbers, so you can see it as this way, like you take the projection of the graph onto the x-axis as you see the input. The number of the set of the inputs are the whole real line, so we say the domain is all real numbers. And the graph is horizontal line passing through all the points of the form xc. So you can take -2c, -1c. So x changes, but c is constant. And let's look at this function. We call this function identity function. It's f of x equal to x function is an identity function. This identity is coming from one property, but we will not tell you this one now. It's not for this section, but we will see it in the inverse function section. Now, if you draw the graph of this function, you will get y equal to x. The graph of y equal to x, you can make y is equal to x, then there will be 0, 0, 1, 1, minus 1, minus 1. And when you put them, you will see this is a line equation. This is like mx plus, if you want to write it as like slope plus b, which slope is 1, and this is 0 here. Anyway, you can do it in any way. It's a line, and you can look at the domain. The domain is, we take the graph and we look at the projection of the points here onto the x-axis. So you see the domain is all real numbers. So inputs are all real numbers, and you can see here, you can put any x value here, any real number, and it's okay. And the range is all real numbers again. So the outputs are, you see from the graph you projected onto the y-axis, you get all the range here as all real numbers. And it's a straight line. Its graph is a straight line passing through 0, 0, and 1, 1. And the other thing is it's an increasing function from left to right. If you go this way, it's going up. So then it's an increasing function. Okay, square function. Look at the square function. This is f of x equal to x squared, and when you draw the graph of it, it corresponds to the graph of y equal to x squared. And when you draw this one, you will get such parabola. We will call it parabola. We will see its properties in the second semester. Yes, and you can look at the domain. So what's the domain? It accepts all numbers here, all real numbers. And also you can see it from the graph. So its projection onto the x-axis is the whole real line. So you say the domain is all real numbers. And also you can see it from the formula. You can put any x here. You can take the square of any real number, and it gives only one value. So there's no problem. And the range, okay, look at the range. You take the projection of the curve onto the y-axis. So you see only this part. So this corresponds to the range from 0 to infinity. And it's an even function. We can verify this. Now look at this one, f of x equals x squared. And f of minus x is minus x squared. And then this becomes x squared. You know, the square, we take the square of the negative sign here, it will be positive. So they are same. They are same. So that means f is even. Okay, this was the verification of it. And if it's an even function, its graph will be symmetric with respect to the y-axis. As you see, it's symmetric with respect to the y-axis. So this is, and it's increasing here and decreasing here. And it's symmetric with respect to the y-axis because, okay, it has to be y-axis because it's an even function. Now let's look at the cube function. Cube function is f of x equal to x cubed. And if you want to draw its graph, you just replace f of x with y. Then you can take this table, you can make the table, and you put 0, it gives 0 cubed, and minus 1 cubed, you know. You find the order pairs, you put them here. As you see, you will get the graph. And from the graph, you can understand, you can tell the domain here is all real numbers. So the x can be any real number. So we say the domain is whole real line, and the range is also whole y-axis. So it will be, the outputs will be any real number. Its range will be all real numbers. And it's an odd function. Okay, let's see. Let's check the criteria. This f of x, write it. It's x cubed. Check f of minus x. It's minus x cubed, which makes minus x cubed. And minus f of x, it's minus x cubed. This becomes minus x cubed. You see they're same. So they are same. So if they are same, what do we say? Same. So f is odd. So you see these two, if these two are same, then we say it's odd. Now we verified it's odd. So one other thing, if a function is odd, then its graph is symmetric with respect to the origin. As you see here, there's a symmetry here. 2, 8 is here, and look at its reflection through the origin. It's minus 2, minus 8. It's on the graph. So for each point, the reflection with respect to the origin is also on the graph. So it's symmetric with respect to origin. And you can tell this one by using by checking the oddness. So if it is odd, so you can directly say it's symmetric with respect to origin. And the other properties, do we have more? Increasing everywhere. So it's when you go from left to right, so it goes up, you know, so always increasing, and symmetric with respect to origin. We already said that. Okay, the square root function, its formula is given this way, and if you want to make its graph, you write the equation y equal to square root of x, and you make the table, and you put the numbers here. Okay, let's be careful here because we cannot take the negative values of x, because the negative values here will give you complex numbers. They're not accepted. So minus 1 is not accepted. As you see, the graph does not have no graph here. So no graph because x is negative here. So negative x is not included, not in the domain. Now for the other part, so you can take the positives and zeros, 0 and positives, like 0, so you square root 0 is 0, so take 1 and square root 1 is 1. And you can use some calculator to do the other numbers, and you will get such a graph. Now obviously the domain here is only the positive x values and 0, and the range is all positive numbers and 0. and f is from left to right, it's going up, so it's increasing. Okay, I think that's about it about the square root function. And let's look at here the absolute value function, f of x equal to absolute value of x. And if you want to make its graph, you look at this, you make the graph of this equation. You replace f of x with y and you make the graph. You can make a table and put the numbers here. -2, it will give you 2, -1, it will give you 1, and 0, 0, 1, 1. Anyway, you can take lots of points, and then you will end up with this graph. So the graph is a clear V shape here. From the graph, you can tell the x's. Okay, all x's are accepted here. You can take the negatives and positives, no problem, because absolute value take care of this one here. X can be anything. So also from the graph, you see the projection of the graph onto the x-axis is the whole real line. So that you say the domain is all real numbers. And when you take the projection onto the y-axis, you see the range is all the range is all positive and 0. So the range is the set of all non-negative numbers, which means 0 to infinity. And okay, the absolute value function can be written as a piecewise defined function. If it is less than 0, it behaves like -x, and if x is bigger than 0, it behaves like x. So we have this, we can see this one in the graph also. This part is y is equal to -x line, and here is y is equal to x line. Okay, think of this, like remember how to do the graphs of the piecewise defined functions. And it's an even function. Okay, it's an even function. You can see that this way f of x is equal to the absolute value of x, and this f of -x is equal to the absolute value of -x, and which is by the property of absolute value of absolute value function, it's equal to the absolute value of x. And I want to say a common mistake. It's a common mistake. No, this is not true. Some students write it this way, it's equal to x. No, it's not. So it might be equal to -x, it might be equal to x, so it depends on what x is. So when you look at these two, they're same, so you say they're same, so f is even. And if f is even, then its graph will be symmetric with respect to, so this implies it will be symmetric with respect to y-axis. So it's here. So you see this one here. This is symmetric with respect to y-axis. So if you have this point, its reflection through the y-axis is also on the graph. So you see its reflection with respect to the y-axis, it's on the graph. So it's a symmetric. It's a graph symmetric with respect to y-axis. Now you can tell this one from the evenness. So if a function is even, then its graph is automatically symmetric with respect to the y-axis. Okay, we already said that. Now f is decreasing, okay, from left to right. Always you go from left to right. So it's going down. Going down means decreasing on this part and then increasing on this part, up. So it will be increasing on the positive part, decreasing on the negative part. Now we will see the piecewise defined functions. Some functions are defined piecewise. Piece means qism. So in different qism, in different pieces of the real line, the behavior of the function is different. So for example, if the input is negative, for the negative x values, we use this formula, x squared. So here, if x is bigger than or 0, if your input, the input here, you put a number here and you check if it satisfies this condition or this condition. So if it is bigger than or equal to 0, so you use this formula. Now, when you have x here, first you have to check which one, this one or this one. You go to the condition, then you apply the formula. You apply the formula. Now, let's see that on the example. So it says, for this function, find f of minus 3, f of 0, and f of 2. Let's check f of minus 3. First, your x is this. Now you check which one applies. Which one? So you say, which one is true? Like minus 3 is bigger than or equal to 0? Yes, is it? No, it's not true. False. So then you don't apply this one. So yeah, if is x less than 0, so minus 3 less than 0? Yes, it's true. Then you say, I will apply the first rule. The first rule is what? X squared. So it has to be minus 3 squared. Then the answer will be 9. Now let's look at the 0 here. 0. Now your x is 0. Now you check which one is true, this one or this one. Now 0 is bigger than or equal to 0. That's true, because we have this option here, the equal option. So 0 is equal to 0. It's okay, it's true. Like 0 bigger than 0, it's false. So we don't take this rule. The condition is not satisfied, so we'll use the second formula. The second formula says you have to use x plus 1. So it has to be 0 plus 1. So it will be 1. Now when it comes to 2, now your x is 2. So which one is true? So 2 is less than 0? No. The first option is eliminated. In any case, you have to check all options. Okay, it might be 3 conditions here, and check all of them, and it might not satisfy any of them. So in this case, the function is not defined at this point. Now look at here, 2 is bigger than 0. That's correct, so true. So we apply this formula here. So the formula is 2 plus 1, which is equal to 3. So we evaluated these. Now let's look at this try and check problem, and then please stop the video and try to do it by yourself. For the following piecewise defined function, evaluate f of minus 4, f of 0, f of minus 1, and f of 3. Now for f of minus 4, you check the conditions here. So your x is minus 4. Now which one is true? So you check these two things. Minus 4 less than minus 1, minus 4 bigger than or equal to minus 1. So this is for sure it's true, and this is false, right? It's not true. So in this case, you have to use this rule here. So you use this rule, so it will be negative 4 cubed, which is negative 64. Now for the other problem, we will do the same thing. F of 0. Now our input x is 0, so we check which condition applies here. Then you check the x here, 0. 0 is less than minus 1. 0 bigger than minus 1. So which one is true? This is false. 0 cannot be less than minus 1. False. And this 0 is bigger than or equal to minus 1. Yes, it's not equal, but it's bigger than. So in this case, it's true. So we use this formula. The formula is 0 squared, which is 0. So if you have more, you have to try them. Unless you get true, you don't use any formula. So if you don't get any true, then it means you don't apply And in formula, you just say the function is not defined at this point. Okay, let's look at the other point, f of -1. So f of -1, check here these two. Which one? -1 is bigger than -1, less than -1? No, this is not true. -1 bigger than or equal to -1? Yeah, that's correct, because we have an equality here. It covers the situation, so it's true. So we use this formula here, is the x squared, so it will be -1 squared, so it will be 1. So let's look at the other one, f of 3. Now again, you will go to here, you will check 3 bigger, less than -1, or 3 bigger than or equal to -1. Is this true? It's false. So is it true? Yes, it's true. So we use this formula here. The formula is x squared, so we have to say 3 squared is equal to 9. Graphing piecewise defined functions. Now let's look at this example. Sketch the graph of the piecewise defined function. So we have a piecewise defined function. The function behaves different in two parts. It's when x is negative or equal to 0, it behaves like x squared, and when it is positive, x is positive, strictly bigger than 0, it behaves like x plus 1. So how should we sketch the graph? So if you already know the graphs of these functions here, y equal to x squared and y is equal to x plus 1, it's better you make their graphs separately. You can make the graph separately like this, and like, I don't know, it should be something like this maybe. Yeah, it's better you do their graph separately. Then you take the pieces and paste them together. First, sketch y equal to x squared, sketch y equal to x plus 1. You can make a table, and put the points. This makes a line, so it will be line. This is like a parabola, it's curvy. So you put the order pairs and you find this graphs. Then after you find the graph, you sketch the graph separately. Now you pay attention to the pieces. I mean, which pieces of the real line we should take. Now after sketching the graphs of y equal to x squared and y equal to x plus 1, we will take only some parts of these graphs. So which parts? So this conditions are telling us the parts, which parts. So here it says you have to take the part where x is less than or equal to 0, and here it says you have to take the part of the graph y equal to x plus 1 where x is bigger than 0. So let's look at them here. So where is x? When x is less than 0, we take the graph of x squared. So x is less than or equal to 0 means this part here, right? So we take this part of the graph. Now from the other graph, we take the x bigger than 0 part. So x bigger than 0 part is this part, as you see here. It's this part. So we take this part, and then we take them and we combine them. We put them in the same graph. So we take this piece and put it here, paste here, and you take this one, paste here. And about the equality here, as you see here, there's a empty, and this is empty, and there's the full here. So why is that so? Because it says x is bigger than or equal to, so you take this point here, full from here, and it's also full here in this line, but since x equal to 0, 0 is not included here, you take this one as empty. So when you combine both. Okay, let's look at this try and check example exercise. It says sketch the graph of piecewise defined function f of x equal to x cubed if x is less than -1 and x squared if x is bigger than or equal to -1. First, okay, let's sketch the graph of y equal to x cubed. And if you don't know it, you can make a table and set the values for x and y. And if you know the graph already, you can do it. So it's y is equal to x cubed. Yeah, should be like that. And y is equal to x squared is like this. So y is equal to x squared is a parabola. Y is equal to x squared. And here is x cubed. Then we have to take the part which x is less than -1. So here x is less than -1. X is where? It's -1 is here. So we take x less than -1. So it means we take this part here. So it means we're taking this part of the graph. And for this part, I mean for x squared, we take the part where x is bigger than -1 or equal to -1. So look at here, -1 is here. So it corresponds to 1 because -1 squared is equal to 1. And x is bigger than or equal to -1 means we are talking about this part of the real line. So we take this part of the graph. And here we take this point as well because it's full. We will take it as full because there's an equality here. So when you put them together, I mean when you put these together, you will get this line here, I mean this graph here. Up to -1. So you can look at here, this -1 corresponds to -1 here because -1 cubed is equal to -1. So this is x and this is y. And we take up to -1, so it comes up to, okay, here is -1 and here is -1. So it goes up to this, and we take this one empty because x is not included in the graph of x cubed. And then we take this part here after -1. Now it means this part. So at -1 it takes the value 1. It's 1. So then we take x squared. And this gives us the graph of, this is the graph of y is equal to f of x. And here f of x is this piecewise defined function. So this is the final answer now. Okay, it's done. Okay, do we see piecewise defined functions in our lives or in the applications? Yes. This is one of the examples. Let's look at this example. A cell phone company uses the function below to determine the cost C. So the C is standing for the cost in dollars for gigabytes of data transfer. So the cost for gigabytes. So this is a function CG, the cost of gigabytes. And now if the gigabytes is between 0 and 2, you pay, the cost is fixed, it's 25 real. And now if the gigabyte used or transferred is bigger than 2, so you pay some extra to 25, and here's the formula for the extra. This is 10 times t minus 2, 25 plus 10 times t minus 2. So here, find the cost of using 1.5 gigabytes of data and the cost of using 4 gigabytes of data. So it's simply asking C 1.5 and C4. So you have to check 1.5. 1.5, is it here or here? So it's definitely 1.5 is between 0 and 2. So this is true. So we apply this formula. So what's the formula here? So you don't see any key here. So it's directly 25. So you write 25. Now look at C4. So 4 is bigger than or equal to 2. So bigger than 2. It's okay. So this is true. This statement is true. And then you put 4 here. So you got 25 plus 10 times 4 minus 2. And which gives us 25 plus 10 times 2, which makes 20. So it makes 45 real. And let's see how the solution is given in the slide. Okay, and most of the time, like a computer programmer writes this formula to the computer, and the computer calculates the cost, and it tells, or it sends the bill to you. You know it then. But the background is you use some mathematics, as you see. So this is what exactly I'm telling. So yeah. Okay, thanks for listening.